is the difference between intrinsic and extrinsic properties. Can anyone give me an idea of what an extrinsic property is? What are the difference between the two then? Very quiet. Definitely have to unplug that phone. So, no idea? Extrinsic, intrinsic properties?
Is extrinsic something that can be seen and intrinsic something like internal?
Sort of, yeah, sort of. Yeah, that's not a bad start. Extrinsic is something that can change, and intrinsic would be something that doesn't. So what would be like an example of a property that's extrinsic, something that can change? An extrinsic property of a substance. Let's say we have a substance like water. Just take water. What would be an extrinsic property of water? Something that can change about it.
Temperature?
Yeah, definitely. We can change the temperature of it whenever we want. We can heat it up. We can cool it down. And the temperature of water doesn't really give us any indication of what substance it is. That's another good definition of intrinsic and extrinsic. An extrinsic property doesn't really give us any additional information to try and identify what it is we're talking about. If I say something, an object is 50 degrees, well, that could be anything. So temperature, that's an excellent one. And any other ones? Volume. Yes, John, volume. If I said something had a volume of a liter, is it air? Is it water? Is it corn syrup? It could be like a big piece of metal. You don't really know what that is either. It could be, we could increase it, we could decrease it. So volume is another one. So we have temperature, we have volume. Anything else? Right, Adrian, yeah, either weight or mass. I would say mass, because weight, you get into some perilous, perilous spots when you're talking about weight, because something could be a different weight depending on where you are, but it's always the same mass. Yeah, so a mass also is something that's extrinsic. A lot of different things can have the same mass, and so, yeah, mass doesn't really help us figure out the identity of something. Anything else? So we have volume, we have temperature, mass.
Color?
Color, that's interesting. So can we change the color of something without doing something chemical to it, without changing its chemical properties?
No.
Yeah, probably not, right? I mean, we can do lots of reactions that involve a change of color, but actually color, I would argue, is something that's intrinsic. Like gold is the particular color that it is. And if I have a pound of gold, or if I have a gram of gold, it's the same color, right? I really can't change the color of it unless I do something to it, unless I react it with something, and then I can change the color. So I would argue that color is actually intrinsic. It's one of the more important intrinsic properties. Adrian says length. Yeah, length is also an extrinsic property. Lots of different things can have the same length. Okay, so let's look at what are intrinsic properties, properties that can help us identify something. Another definition is it doesn't matter how much of the substance we have, this particular property will always be the same. Sort of like I mentioned with gold earlier. It's always going to be the same color. If it's 100% gold, 24 karat gold, it's always going to be the same color regardless of how much of it I have. But what's something that doesn't change depending on how much I have?
Density.
Density, exactly. There we go. And interestingly, we can take two extrinsic properties, which are the volume and the mass, but the ratio between them is an intensive property. That's the density. So yeah, very good. So the density of something is something that helps us identify a substance. Like the density of water is very specific at different temperatures. And as we'll find out today, if we add something to it, if we create a solution with different amounts of sucrose in it, the density changes, and the density changes in a very specific way. And that density helps us identify that substance as 0%, 10%, 20%, 30%, whatever the percentage is, it'll have a specific density. Anything else?
The hardness.
Hardness. Excellent. Yeah, that's another good one. Hardness. The hardness of a diamond is not dependent on the size. So I can have a really itty bitty, probably can't even see it. I've got like a tiny 1/10 of a carat diamond in there. You can't really tell, but it's super, super, super small. But it's the same hardness as, you know, the Hope diamond, which is like over 100 carats. So Jean, yes, an extensive property is based on the amount of the substance. That's absolutely right. So like the volume, or something we can change like the temperature, but usually it's based on the amount of something. So are there any other intensive properties you can think of? Hardness was a good one. I hadn't thought of that one.
Boiling point.
Boiling point. Yeah. Boiling point. Excellent. That is also a property that we use to identify something. So the boiling point of water is 100 degrees Celsius at sea level at a particular pressure. So if we have a lot of water or we have a little bit of water, that boiling point doesn't change. And even when we mix it with another substance, the boiling point doesn't change. So if we have alcohol and water mixed together, the alcohol will boil first at its boiling point, and then the water will boil second at its boiling point. Excellent. That's a really good one. I was also thinking that the state of a substance is intensive as well, because water is a liquid at between 0 and 100 degrees, and it doesn't matter how much you have of it, it's going to be a liquid. Neon is going to be a gas, regardless of how much you have of it. Iron is going to be a solid. So the way to think about it is that things that change with the amount of a substance are extrinsic properties, and things that don't change as you change the amount of a substance is an intrinsic property. So we're going to be looking at an intrinsic property today, which is the density, by looking at two intensive properties.
Is that the same thing as extensive and intensive?
Yeah, I'm sorry. Depending on what side of the pond you're from, intensive or intrinsic is the same as extensive or extrinsic. Oh. Sorry, I gotta get my American down a little better. I sometimes trip up when doing this. As you'll notice that sometimes Suzanne sometimes slips German words into her presentations without knowing it. So.
Are you not American?
I am not. You may be shocked to hear. No, I'm one.
Canadian?
I am. I am indeed. So, since we're going to be doing some actual chemistry today, it's kind of important to have these on hand. I know we're only dealing with sugar, but you get some sugar in your eye, certainly wouldn't want to be you. Just so we can say that we did all we could for safety. So the first thing we're going to do is determine the density of a solid, and we have 3 different solids. Hopefully everyone has a little bag here with exploring density on it, and there's 3 small cylinders. One is polyethylene, one is aluminum, and I forget what the other one is. Teflon, I think? Probably Teflon. And so we're going to measure them. So that part will be fairly straightforward. We're just going to determine the volume by actually measuring it ourselves, and then using the mathematical expression to volume is determine the volume of a cylinder. We'll just use that equation and figure out the volume and then get the mass. So that one will be extremely straightforward. When you have the density of that, basically then we're going to use that later on when we look at the densities of our different solutions. Has anyone made their solutions already? Or did you have stuff to do this morning? We'll go over how to make them. I was wondering if anyone did them ahead of time, because it takes a little time to do it. So this part we can dispense with fairly quickly, but then we're going to be determining the densities of solutions, and that's going to take a while. So why don't we just go over basically how we're going to do the experiment. Now, why do you think when we're going to be doing a plot of our data, we're going to be measuring the mass of our solutions at different volumes, and then we're going to plot them? Why would we do that rather than just taking, say, 50 mils of a solution and measuring its mass and getting the density that way? What's the advantage of taking multiple measurements?
We get the average.
Yeah, we more or less remove some of the error we would get with any one measurement, because as we've seen, measuring anything, there's going to be error in that measurement. And so the more measurements you have, basically what happens is that the error tends to, instead of getting larger and larger and larger, if we do our experiment properly, we should have errors that are slightly above, errors that are slightly below. And when we average them all out, we'll get a smaller error than any one measurement would have given us by itself. You've probably noticed that when you did the measurements last week, when you were determining the mass of the cup, and then you were looking at the variations from one measurement to another. Did you notice that the average variation was pretty much smaller than most of the individual variations? Was that true for pretty much everybody? So quiet. Adrienne says yes. So did people get like a higher, was their average variation less than most of the variations that they looked at?
Yeah, but for one of them, it was around the same.
Yeah, but actually for some people, their average variation was nothing, because they had some that were slightly above the average, some that were slightly below the average, and then some that were right on the average. And then when they added them all up, they got 0. And that's basically what we want to do here. By taking a number of measurements, we're going to reduce the error in any one of those measurements and hopefully reduce them almost to zero if we can, you know, do a good job. So anyone tell, we get what's called a best fit line. So what does that mean? What is a best fit line? When you're plotting something, what is a best fit line?
The line that fits best with all of the dots.
What do you mean by it fits best? What would that mean? What does that mean to you?
Like, it's kind of like the average of the distance away from the dots.
Oh, there
So
you
like,
go. So basically, let me see. Hang on, I think I left my marker somewhere. I'll be right back. Okay, I found another one. So basically what we're talking about is when we plot something, let me draw here. So when we plot something, we want to look for the relationship between X and Y. Man, this is a bad one. Hopefully I'll find the other one soon. So we plot, we get all our data points. And then our best fit line would be the one that goes through, oh man, that's not good. That goes through and basically has the smallest distance. If we added all the distances of all the points together from the line, that would be the line that gives us the smallest distance. And basically we measure how good this line is by actually doing that calculation. We'll have the computer do the calculation for us. It's called a regression line, and it's given the symbol R. So a perfect line where every single point is exactly on the line has an R of 1, meaning there's a perfect relationship between X and Y without any variation at all. Very rare you're going to have data that good. So what we look for, we don't even plot R. What we do is we square R, and what we're looking for is an R squared greater than 0.9 generally. Anything greater than 0.9 sort of tells us that the equation we've used to fit all this data is probably the right one to use. And in this case, what's the relationship between X and Y for this particular example? What sort of relationship would you say is between those two variables? So I've got my X, I've got my Y. What sort of relationship between those two do we have?
If one goes up, other.
Positively correlated.
Right, they're positively correlated. That's one way to put it. What's another way to?
Linear. It's linear.
There you go. Yeah, linear, meaning there's a very simple and direct relationship between the two. And when we fit this line, we get a fit of Y equals mx plus b. Now, what is m and what is b? What are those two different things? Oh, here's my marker. Excellent. Let me clear that, put it on a little better. So here's my plot. I've got X here, and I've got Y here. Here's my line with my dots on either side of it. So this, the relationship between X and Y is given this particular equation, meaning we can determine the value of Y at any point by taking our value of X, multiplying it by this number M, and adding this number B. So what is M and what is B?
M is the rise over the run.
There you go. What's it? So it is, yeah, it's Y over X, right? That is the change in Y over the change in X. Yeah. So what's another way of putting that? Rise over run. There's another word for it. There's a couple people in the chat have it. The slope. It's the slope. It's the slope of this line. Yeah. So M is the slope. And it's a small m rather than a capital M. Capital M, we'll find out later, is a whole different meaning. What's our plus B? What's this thing?
The y-intercept.
Right. It's right here. It's wherever when we draw our line out. It's wherever it bangs into the y-axis when x equals 0. So if we don't measure what the value of y is at x equals 0, basically when we give our when we look at our data and plot it out, it will determine what the value of y should have been, most likely, at 0. We don't know what it was because we didn't measure it, but it gives you an idea. And so if our y-intercept is way off, if we're expecting a y-intercept of 0 and we get a y-intercept up here, we've probably done something wrong. So it's important to look at both of those. So this is linear. Why do we say that this is linear? What does that mean? What does a linear plot even mean? Yes, we get a line, but why? Why do we get a line? How come we don't get something that looks like this? Or something that looks like that? Oh, Amanda, yeah, because the change is constant. Excellent. Yeah, that's a good way of putting it. Basically, it means that for every change in X, there's the same change in Y. So if X goes up by a factor of 2, Y goes up by a factor of 4 or 5 or 6 or whatever it is, but it's always the same. So if X goes up by a factor of 2, Y changes by a factor of 4. When X goes up by a factor of 4, Y goes up by a factor of 8. It's always the same increase. It doesn't necessarily mean that it's 1 to 1. It could be 1 to 2 or 1 to 3 or 4 to 5. It could be anything, but it's always the same, whether X is large or whether X is small. It means it's linear. Excellent. And we'll find today that that is what our plot should look like. What are we going to plot? So we have X here and we have Y here. What is it we're going to plot? If we want to determine the density, what is it we're going to put on the x-axis and what are we going to put on the y-axis?
Mass and volume.
Where are we going to put mass? Where are we going to put volume?
Would mass be y and x be volume? I mean, x, no, yeah, mass be y and x be volume.
Okay. Why? Or how come? I'll put it that way.
Because, well, I'm just guessing, but because it's like rise over run, meaning
Mhm.
the rise is the y, the run is the x, and then
But
mass over volume.
why is this? But why is it mass over volume?
Because the density.
Well, that's one reason. Yes, the one reason is the Xiaohui said here. Since density is equal to the mass divided by the volume, we want to have the mass as y and the volume as x, because as we mentioned just a minute ago, the slope of the line is the change in y over the change in x. And since we want x to be in the denominator, and we want y as the numerator, we want mass over volume for our density. So what will be the slope of this line?
The density.
It'll be the density, exactly. So if we measure, that's what we're going to do. We're going to measure the slope of the line for a number of different solutions today. We're going to look at, so we're going to have our volume over here and our mass over here. And so we'll look at just water, and then we're going to look at 10% sucrose, and then we're going to look at 20% sucrose, and then 30%, and then 40%, and so on. And the slope of each one of those lines should be the density of those solutions at whatever temperature. You should also make sure you measure the temperature of the room, because you will get, everyone here will probably get slightly different results because the density is dependent on the temperature. So that there's a relationship between the density and the temperature. What happens to the density as temperature goes up?
Does it get smaller?
It gets smaller, right, exactly. The more energy we put into our solution in the form of heat, those molecules start moving around faster, and they create more space in between them. So the density will get, as we saw when we looked at, we measured, we had a table for the density of water last week. You notice that it changed, not a lot, in a subtle way, but it changed as the temperature got higher, the density got slightly smaller. And that's true for pretty much everything. Gases, solids, liquids, they all do that. So what is the dependent variable here, and what's the independent variable? Anyone tell me what the dependent variable is? What does that mean? Dependent variable and independent variable.
The volume would be the explanatory variable, which is the dependent variable.
Okay, so you're saying in this case,
I mean, no, independent. Sorry.
you're saying it's independent. Okay.
Yeah, because it's
So that would make mass dependent. So why is that?
I just remember in stats the x was the explanatory variable, the x-axis. So, and then explanatory variable is the independent variable.
I love that. Explanatory. I haven't heard that one before. So which one is explanatory? X?
X, yeah.
And so what does that make Y?
Explanatory and response.
Oh, in response. Oh, there you go. Yeah, actually, I kind of like that better than independent and dependent, because I find students get very confused. I get confused about it too sometimes, independent and dependent. I like that explanation a lot better. Because what does independent mean? An independent variable. What does that mean? Oh, yeah, Sean said, yeah, the mass is dependent on the volume. Yes, but you could also say, is the volume dependent on the mass? Or Yes or no?
No.
Not really. I mean, a good way of looking at it, if you don't know the difference between independent and dependent, the independent variable is the one that we can independently vary. So in other words, I can measure whatever volume I want. I can pick 5 mils, 10 mils, 100 mils, 1,000 mils, 58.6 mils. I determine that. I get to pick whatever volume I want. But I can't pick the mass. I can't, because the mass is going to be dependent on whatever I choose as my volume. So if I choose a volume here, that basically determines what the mass is going to be, and not the other way around. So it is a little weird, because like when you think of, I sort of grew up thinking dependent means that the result is going to be dependent on that. I mean, that's the way I always thought about it. But the better way to think about it is like, which one can you independently vary? And in this case, we can independently vary whatever volume we want to measure. We can measure whatever volume we want, but the mass is going to be dependent on whatever volume it is we pick. So that's really the way to look at that. Oh, let me undo. So what should our y-intercept be for all of these measures? For all these different plots that we're going to do, what should the y-intercept be? Are they all going to be different? So is the y-intercept dependent on the density?
They're all going to be different because they're dependent on the volume, right?
Okay.
Because the graphs, it says like 5 milliliters, 10 milliliters.
Right, but remember the y-intercept is the place where x equals 0. So at 0 volume, so 0 mils of volume, what should the mass be for all these different solutions?
0.
Yeah, they should all be 0, right? Because what's the mass of not anything? Nothing. You know, if I have no iron, the mass is 0. If I have no oxygen, the mass is 0. If I have no solution, the mass should be 0. But we'll see that if you don't measure that, that's introducing some error, because we're not going to have a perfect plot every time where every single measurement is exactly correct. There's going to be a little bit of error, particularly I think when we're measuring the small volumes, because it's kind of hard to measure the small volumes. When we get to like larger volumes, I think the error is probably somewhat less. So it'll give you an indication of how accurate your measurement can be. And we could also include that number in our plot and see if it makes the answer any different. So we can leave out 0 and 0, and we can also include 0 and 0 and see if that changes the slope, which is our density at all. Okay. All right. So let's go and see how we're going to do this experiment. So we sort of went over how to plot these. These are the different materials we're going to need. Does everybody have sugar? It's just that's not included. I had some white sugar, but it had some other stuff in it. I think we had put some vanilla in it at some point, and so my solutions were a little darker probably than they should be. So when you do your lab report, you put that down as a source of error. Like if you have brown sugar, that's sucrose and a whole bunch of other things in there as well. So everyone has white sugar, hopefully. Their bottle, their water, of course. I'm just using filtered water. My non-diet beverage, I have some grape juice that I'm allowing to come to room temperature. That's going to be important. And then as far as graphing, what do most people feel most comfortable using as far as graphing is concerned? Give me a sort of hint as to what people use for plotting. What programs have you used in the past?
I don't know what it's called. It's like the Google equivalent of Excel.
Oh, Google Sheets. Yeah, I was going to show you how to use Google Sheets today, because that basically does everything we're going to need for this. But do people have Excel? Some people have Excel.
Could I use Stacky?
You can use whatever program you want, as long as it will give you a linear fit to your data. You can use whatever you like. I mean, anybody who's free from the shackles of Excel, I will not give you any grief. I've been using Excel for like 30 years and I'm still not comfortable with it. So you can see what a great program that is. But if you have Excel and you're familiar with using that, that's great. If you have something else, that's great. I was sort of basically going to take you through Google Sheets because everybody has access to Google Sheets. Although I think because you're Skyline students, you are eligible to get a free Microsoft Office for either PC or Mac. Were you guys aware of that? So you can get Microsoft Excel if you want it, and it's free. So it's worth every penny. But like I said, I'll take you through Google Sheets because everybody's got a Google account, and it's fairly straightforward. It doesn't give you it doesn't have all the bells and whistles that Excel has, but basically what we're doing here, we're just looking for a linear fit. So it does that just fine. So when you're making your solutions, there's a couple things to remember. So remember when we were taking the mass using our little balance last week. This time we're going to be using something called a weighing boat. So everyone found their weighing boats. Can you use milk as the beverage? No, because that has proteins and a lot of other things in it. And basically, so the density won't be determined strictly by the sucrose content. I mean, the best thing would be like, Kool-Aid or just some sort of fruit juice, like a clear fruit juice, because you want the density basically to be determined only by the sucrose content. And milk has got fat in it, which is going to decrease the density, and it's got protein in it, which is going to increase the density. So it's got both those things. Yeah, so everyone has their weigh boats. I need to go grab mine. I'll be right back. Okay. All right, so when you're using these, the thing to remember, so come down here and look at it. So the thing to remember with these is that you want to put it on the balance and then tare. Remember we talked about tearing last week. So we put it on top, and then we'll get a mass, a small mass, like around 2.3 grams or so. And then we just hit tare till it goes back to zero, basically just subtracting the mass of the weigh boat, as you see my dog in the background there. So what we're going to do is take, even right here, we've got the different masses of sugar for you to use. So we want to get 7 cups actually, one with just the filtered water in it. And then in the others, we're going to put 5.5 grams of sucrose, 12.5 grams, 21.5, and so on. So these are sort of basically designed to empty. You just, when you pour it into, you can even curl up the sides a little bit like that, and then just let the sugar go into the cup, and then add your water. And I found when I was making these this morning, I made 10, 20, 30, and 40, that it helps if you heat them a little bit. Because they're not going to dissolve, especially as you get up into the higher percentages of sucrose. They won't go into solution at room temperature by themselves very easily. So if you nuke them for about 15 seconds and then stir it and then sort of let it cool down a bit. And if it's still not in, give it like another 10 seconds and then stir it. But remember, you're going to have to let that come down to room temperature. So that's why I'm saying making these solutions is going to take a while. So you may want to, we may want to do what we can together, and then doing some of this, like the plotting and doing the measurements and making the solutions and determining the slopes of the lines. Maybe we'll, you can do that later. But if you want to get started on it, you can certainly go right ahead. I'll give you guys about 20 minutes to work on it or so. But then when you make your solutions, like I said, you really need to let them come down to room temperature, because as you pointed out, density is dependent on the temperature. And so if I have a bunch of different temperature solutions, the density is going to be determined now on 2 things rather than just one. Instead of just the percentage of sucrose, it's also going to be dependent on the temperature. And so we want to avoid we want to have basically one variable. When we plot our volume versus our mass, we want the only variable to be the percentage of sucrose. That's it. That's the only variable we want. If we introduce another one, then we're going to see a whole lot of scatter in our data and a lot more error. And so this is a way of eliminating as much error as possible. It says in the instructions, the sucrose in the 50 and 60% solutions will not dissolve easily. I'm saying that pretty much all of them won't dissolve that easily. 10 and 20 go into solution fairly readily, but the rest take just a little bit of heating. Don't heat them so long that the cup melts and it starts boiling. We definitely don't want that. Just for a few seconds, like they suggest, about 10 seconds, maybe a couple of bursts of 10 seconds each, okay? So, all right, so what we'll do is take about 20 minutes if you want to work on making your solutions, and then we'll come back and get started on. I have coffee with 15 grams of sugar. Yeah. I mean, obviously, coffee is going to have a lot of other stuff in it too, but Gatorade's perfect, Jonathan. That's what we're looking for.
Professor?
Yes.
How about Snapple?
Excuse me?
Snapple?
Snapple. Yeah, perfect. Basically, we want to have like a clear liquid. Basically, all we're looking for. Or if you have a soda, basically, shake it up, let all the CO2 come out, let it go flat and come to room temperature, and you can use that. So if you have like Coke or Sprite or RC Cola or whatever it is you have, you can use that, because I mean it's not a clear liquid, but the amount of other stuff other than sugar in there is going to be very small. So it'll be a little bit of an error, but not very much. So I think coffee's fine.
Can I squeeze lemon into water?
Yeah, I mean, if you want to make some lemonade, you should go right ahead. Yeah, that's fine.
How important is it to have the drink to be a little transparent?
Well, just basically you don't want any solids in it. That's all. I mean, it can be a colored liquid, but like orange juice with a whole ton of pulp in it, you know, maybe run it through a coffee filter and then use that.
I see. So the tomato juice that I have probably won't work.
Mm. Yeah,
Or won't be
tomato
ac-
juice has a lot of solids in it. Um, maybe try filtering it. You don't need that much.
Um,
You just need like 25 mils of it. So
Adding water, perhaps?
yeah, that still doesn't get rid of of the solids.
Okay, that's fine. I have other drinks, so I'll just pull it out.
Yeah, what else do you have?
I have orange juice as well, except
Well, there you go.
I wanted to drink it, so
Well, like I said, you only need like 25 mils. That's like less than an ounce.
yeah, I'll just use that. Thank you.
So yeah, that's not very much. Yeah, it's not a whole lot. Okay, so we'll take like a 20 minutes for you to go and start making your solutions, and then we'll come back together and we'll look at doing the first part, how to do the first part, and then basically what I'll take you through is I'll go through some of the data I came up with this morning when I was doing it and how to plot it and what you're going to do with that. And then that's basically it, because we determine what the density of our solid objects are. We determine what the density of our solutions are. And then the third part is just trying to determine, well, if the density, knowing what I know about the density of my solid objects and my liquids, is it going to float on it or is it going to sink? So what do you think that's based on, whether or not it's going to float or whether it's going to sink?
If it's more or less dense than water.
There you go. Exactly. Yeah, so I think we're going to find that like metal is going to sink regardless. But depending on the density of the Teflon and the polyethylene, they might float on some of these. I haven't tested it yet. That should be fun to try. Pomegranate juice, yeah, that should be okay. I don't think pomegranate juice has a whole. You can basically see through it, right? Basically anything you can see through that doesn't have a bunch of pulp or solids in it is fine. I mean, if you're stuck and there's nothing in the house at all, then yeah, use whatever you want. But make a note in your lab report that, you know, this particular, like milk, for instance, it's going to be affected by the presence of lipids. It's going to have fat in it. I mean, even non-fat milk has a tiny bit of fat in it. Fat has a lower density than water, so that's going to lower the density. It also has a bunch of protein and solids in it. That's going to increase the density. So the density will not be determined by the sugar concentration, whereas with all these other ones, it's mostly determined by the sugar concentration. But like with anything, it's a source of error. If in your report you mention it's a source of error and report it properly as a source of error, then it's all good, right? Because that's what we're learning. That's one of the most important lessons here, is knowing what a source of error is and then trying to either explain how it affects your experiment or attempt to eliminate it. Okay. So I'm going to set my watch for 20 minutes. I'll just pause the recording and then we'll come back. Hopefully people will have at least weighed out their sucrose in the different cups, added the water, and then we can come back and continue. Does that sound like a good way to go? Anyone have any questions before we pause?
Yes, so right now we're just making sugar water. We're not
Yep.
doing anything with the soda right now.
No, we're gonna do that later.
Okay.
Yeah. Basically, all you want to do with the soda right now is just if it was in the fridge, if it is soda, you want to take it out of the fridge, put it in an open cup, and just let it come to room temperature. Because you want it to be flat. You don't because if there's gas dissolved in it, that's going to reduce the density as well, because it has dissolved gas in it, which takes up space. And so you want to get rid of that. So you want it flat and you want it at room temperature. So yeah, so take that 20 minutes, just let it warm up. Okay? And then we'll go over how to, how to take your measurements. Any other questions before we set you off to go measuring things?
Yes.
Yeah.
For me, my inner time went out like as earlier in the labs we're trying to miss some stuff, but for, like right now, we're taking the sugar and we're using this table that I'm seeing from the share screen right now to make those percentages of sucrose to make for this activity, correct?
Right. So the table I've got on the screen right now, we're going to have seven cups, and you mark them with either your wax pen that's included, or if you got a Sharpie, that works too. Just mark them, 0, 10, 20, 30, 40, 50, 60, and then put that mass of sugar in each one. And then we add 50 mils using 50 mils of water, using your 50 mil graduated cylinder. So one thing I want to ask you before we take a little break, what is our percentage of sucrose based on volume or based on mass?
Mass.
Mass, probably, yeah.
Mass, right. I mean, you see it says percentage of sucrose, and then in brackets, W divided by W. I mean, it should be mass divided by mass, but it's weight divided by weight. So yeah, meaning the total weight of the solution you're making, what percentage of that mass comes from sucrose? So when you see, why don't we put 5 grams of sucrose in 50 grams of water to make a 10% solution? Why is it 5.5, do you think?
What do you say to do about it?
What was the question again, Professor?
So why do you think when we make our 10% solution, why do we have 5 grams of sucrose, 50 grams of water? Instead, we have 5.5 grams of sucrose and 50 grams of water. Why don't we just have 5?
Because isn't 10% of 50 5.5? Oh wait, no.
No, it isn't.
No, you're right.
More precise.
Well, what would be the mass of a solution if I had 50 grams of water and 5 grams of sucrose? What would be the total mass?
$55 grams.
It'd be 50,
5.5?
it'd be 55, right? So if I had 5 divided by 55, that's not 10%, is it? It's a little bit less. So that's why we want 5.5 plus 50. Because then the total mass will be 55.5, and then we'll have 5.5 divided by 55.5, and that's pretty close to 10%. So that's why we have the little bit extra, because we need the percent of sucrose is the percent of the total mass, not related to the mass of water, but the total mass. So we need to add a little bit extra to make up for that difference, okay? All right, so let's take 20 minutes. Hopefully, if you've heated, hopefully you'll heat some of these. You could stir them with a spoon, and then hopefully in the time we take is sort of explaining everything, everything will have cooled down to room temperature for you, and then you can get started on your measurements. But let's get started on making the solutions now, all right? So I'll just do a pause, and I'll see everyone back here in about 20 minutes, okay?
Wait.
Oh, go ahead.
Which one do we label as beverage? Beverage. Any of it? The
Yeah,
cup?
so you take, so that'd be like 8 cups. One with just water, and then 10, 20, 30, 40, 50, 60%. And the 7th one, or I guess the 8th one, will just have whatever fruit juice or coffee or whatever it is you're going to use for your solution. Yeah, don't add the juice to anything else. Just keep that separate. We're only putting purified water, distilled water in with our sugar.
Oh, never mind. I found my other cups.
Okay, yeah, there should be a bunch of them in there. I think they give you at least 10. Okay, so is everyone clear?
Yeah.
All right. Okay, I'll see you in a little while. Okay, how's everyone doing with their sucrose measurements?
I'm still weighing my water right now.
Well, it's just a measure of volume of water.
Yeah, I'm still doing that.
Okay. Do people need more time?
Yes.
Okay, how much more time do you think you'd need? Would 10 minutes get you to work where you need to be?
I believe so, yeah.
Yeah, probably.
Oh, Professor,
Yes.
just to make it clear, we're using the balance, right, to balance out how much we need of sugar,
Right. Mm-hmm.
and also how much we need for water, right?
Water, we can just measure that with the 50 mil volumetric with the 50 mil cylinder. So if you fill that up with 50 mils, that should equal 50 grams.
Okay.
Yeah. Yeah. You know, I don't want you using the weigh boats and putting water in there because those are for solids only.
Okay.
Okay.
Oh, and one last thing for
Sure.
I think 60%. I think that's what it was the highest one.
60s.
Is it okay? Is it okay if there's like just sugar on the bottom?
Nope. It's all going to be in solution. Yeah. So just heat it for like 15 seconds, and then use the. I tried initially. I just tried shaking the container. That doesn't seem to work as well as actually putting a spoon in there and stirring it. That works best.
Okay.
Okay. All right. Let's give it another 10 minutes then, and then we'll get back together.
Have some of the sugar here.
Okay. Okay. Hopefully everyone's almost done. At least getting the solutions ready. You may not be ready to measure them for a while until they come back to room temperature. So is everyone pretty much finished? Kenneth, how are you doing? You almost done?
I just put the sugar in the cup. Now I have to do it.
Okay, Arissa, you almost finished?
Yeah, I'm finished.
Okay,
I put my
cool.
cups in the fridge, so I think they're good.
Oh, wait a minute. What's in the fridge?
I could put my cups in the fridge.
Oh, you don't want to do that.
Oh, oops.
Yeah, you want to have them at room temperature.
Yeah, but because they were hot before.
Oh, I see what you mean. You're just trying to cool them down. Okay. Well, you do have a thermometer, so yeah, just basically, yeah, give them like, I don't know, maybe like 10 minutes or something, and then just take them out and just let them equilibrate for like maybe 30 minutes or so.
Okay.
All right. So I figured I'd just go through. We can do the first part of just measuring our cylinders here. So we have 3 different ones. This one's polyethylene, which is just a typical soft plastic. And then this one is acrylic, which is your typical hard plastic, difference between hard and soft plastic. This one's clear and harder. And then we have a cylinder of aluminum. So to measure the volume of these, what do we have to do to measure the volume?
Is it pi r squared times the height?
Yep. That is the volume of a cylinder. Oh, John, if you have a caliper, that's, yeah, definitely use it. Use whatever is the most accurate thing. I don't have a caliper here. But if you have something more accurate, because, yeah, obviously there's going to be a great deal of error using something like this, because we're going to have to estimate like half millimeters and that sort of thing. And even a small difference, like I was just working out my calculations with these just a minute ago. Just the difference between like in 1 millimeter in diameter makes a big difference in the volume. So just, you know, just be ready to assume you're going to make some errors with these. So to get the diameter, basically it's just the distance across, right? And half of that is the radius. So we just measure the distance across. And I am and do it in millimeters, and then we'll convert to centimeters. And I'm fairly consistently getting 12. Or maybe a little bit, maybe 12 and a half.
Wait, are you using inches or
No,
metric?
we do not use inches. Inches is verboten. We definitely want to use metric. Notice that all of our measurements in this class are metric. So definitely we're going to be using metric. So determine your diameter. The tricky part about that is making sure you measure it right in the middle. Try and figure out exactly where the middle of this thing is and measure the distance across in the middle. If you're off even by a little above or below, it's going to be a little bit off. So I'm going to write down my measurements right on the screen here.
Are all the cylinders gonna have the same height and diameter?
They look that way, but go ahead and measure them just to be sure,
Okay.
because yeah, I mean I think they've all been manufactured to do that. So that was my polyethylene diameter was.
The clear plastic, is that soft?
The clear is the acrylic, and then this one is the polyethylene. It's the softer. I mean, it doesn't feel much softer, but it's a slightly softer plastic.
Thank you.
And the height, I got the same thing, like 12.5. But yeah, you want to double check. Actually, it's more like 12.
Is it okay if some of them are different?
Yeah, I mean, of course. I mean, your measurement is your measurement. I'm sure these things weren't made to like super exacting specifications. So yeah, yours may be a little bit bigger or a little bit smaller.
Oh, so for the measurement, you want us to use fractions or decimals?
Definitely decimals.
Okay.
Because we're going to be using these to calculate, right? Because it's V equals pi r squared h. That's our volume. So I've put my measurements in there, but there's a problem. Anyone identify what the problem is?
You put it in millimeters instead of centimeters.
That's right, exactly. Because if I went ahead and did this calculation, my volume would be in millimeters cubed. I don't want millimeters cubed, I want centimeters cubed. Because what is the volume of, what's another expression for centimeters cubed? What's another way of what's another measurement of that volume?
Milliliters.
That's also a milliliter, that's right. That equals 1 milliliter. And that's what we measure density in. We measure density of liquids in grams per milliliter, and we measure the density of solids in grams per cubic centimeter, because they're the same thing. It's just difficult to measure. You can't measure the liquid volume. You have to measure a solid volume, and so we determine that by measuring all these different heights and diameters. So I need to change that to centimeters. So that's going to be 2.1 centimeters in height and 0.625 centimeters is R. So then I'll just go ahead and calculate that. Oops. We got 1.48 centimeters cubed. 1.48. So if my mass is 1.53 grams and my calculated volume is 1.48 cubic centimeters, what's going to be my density?
Oh, wait, Professor?
Yes.
Why'd you put millimeters squared cubed on the bottom?
Because if you give your measurements in millimeters, so like I measured millimeters, right? So I had 12.1 millimeters high and 12.5 millimeters across. I have to convert that to centimeters, because if I don't, I'm going to get cubic millimeters, and that's not what I want. I want it, my density has to be in grams per cubic centimeter. So convert everything to centimeters.
Oh, okay, thank you.
Yeah. And like I said, these are going to be tricky measurements to make, because even the tiniest bit of difference, that's the difference between, like, 12 millimeters and 12.2 millimeters is going to give you a big difference in volume. So it's basically we're squaring the radius. So if you're off a little bit on the radius, then you're going to multiply that by itself, and so that makes the error even bigger. So don't get down on yourself too much if you find out that your density of aluminum is not what it's given. The given density of aluminum is around 2.7 grams per centimeters cubed. So you should get somewhere between like 2.5 and 3.5. If you get anywhere in between there, you're doing great. Right, so everyone's fairly clear on how to do that one? Oh, Jean,
Yeah.
so you did have a caliper? So what measurements did you get? Because yeah, if you have a caliper, you'll get much more accurate measurements than using a ruler. Was it around 12 millimeters? Okay. Yeah, so his measure, so he's using a very accurate way of measuring it, and it came out to approximately the same. So there we go. So go through, calculate all these, and basically what we're going to do is you're going to try and determine, based on the densities you calculate, whether these are going to float in the different sucrose solutions or whether they're going to sink to the bottom. You pretty much guarantee all your aluminum, you're going to sink to whatever solution you put them in. But the acrylic and the polyethylene, those densities are fairly low. As you can see, I calculated 1.03 grams per cubic centimeter for my polyethylene. So I have no doubt that it's going to float on a couple of these, if not most of them. So let's look and see how we calculate our measure volume, measure mass, and then calculate density and start plotting them out.
If I finished, I would start plotting it on the graph.
You have all those done already?
Mm-hmm.
And you did all your measurements? Oh, excellent. Okay. So densities of solutions. Yeah, you can start plotting them. Go right ahead.
So start plotting the density of the cylinders or the density of the solutions.
Well, we're not interested in the density of the solutions. Yeah, why don't you just have a look and see how we're going to do it, and then I'm going to show you how to plot them, because there's a way you're going to want to organize the data to have it all plotted properly. Okay. So the first thing is just once you have your solutions made, and I'm going to use my grape juice that I've sort of let come to, I know it's a weird color for grape juice, white grape juice, I guess. I've let that come to room temperature for about an hour now. So you just measure the mass of your 50 mil graduated cylinder. And we do that so we can just basically just keep adding liquid to this and measuring the mass rather than emptying it out, tearing it again, adding more liquid, dumping it out, adding it back again. This way we can just get the mass of it empty, and then just take the mass of it each time we add some more liquid to it. So my mass of it empty is 29.47 grams. Now I'm just going to assume that that's going to be the same, that mass is not going to change, and that basically the only change in mass is going to be the liquid I add to it. And so you should have one of these transfer pipettes that we talked about before. This will make your life much easier. Get a transfer pipette, and when you're going from water to 10% to 20% to 30%, you should probably rinse it a couple times in whatever the new solution is. So I've got water in this right now. So what I'm going to do is empty it, draw up some of my juice in the cup, and then just empty it out. because I only want juice to be in here. I don't want it to be diluted with any water. So I'll just do that a couple times. Now I know that whatever liquid is in this thing it's just going to be juice. And you can take the 50 ml cylinder off the balance, or you can leave it on, either way. But you definitely want to get your eye. Remember, when we're dealing with these, you want to get your eye at the mark you're going to be measuring. So I want to have my eye at the level of 5 mils. These things hold about 2 to 3 mils. So I'm just going to empty one, empty another, and I'm getting pretty close, and there. So once I've got it to my 5 mils, then I just put it right back down on the scale, and I just measure the mass again. So now I've got 35.21 grams. And I just keep going. Then I add another 5, and another 5, and another 5, and I just keep measuring the mass. And then subtract whatever the mass of the cylinder was in the first place. This just, like I said, this just helps you go a lot faster. So that way we don't have to empty it each time. Although it is going to be a slight source of error potentially. Now I've got 10. My mass now is 40.81. I just keep going until I get to 25. Then I'll plot these. Yeah, it's really crucial to get your eye to that level. There we go. So 15, 45.76. It's got 2 more to go. If you have drops on the side, like I mentioned what we did last time, just tap it on your table and let all the drops fall to the bottom. Because if you don't, then you have liquid basically adding to the mass, but not adding to the volume. So just one more. Then we'll start plotting these bad boys. Okay, almost done. There we go. And last one, 632. Okay, so now I've got my juice. So let's figure out how we're going to plot these things. So like I said, I'm going to use Google Sheets, but you can use Excel or you can use whatever. Oh, are we doing the beverage first? No, I already did the sucrose solutions this morning. I was just showing you how to, the best way to do the measurements of volume and mass. You can do the beverage first, that's fine. Remember to rinse the graduated cylinder between each measurement. So just rinse it with water, make sure you shake all the water out as much as you possibly can, and then do your next one. You don't want to have carryover from one solution to another. So let's go to.
Oh wait, Professor.
Yeah.
So back to table 1 to find the mass gram of the cylinder type. Do we just weigh it, or is that?
That's usually how you determine the mass of things.
Okay.
Yeah, just make sure it's empty. That's the key thing. Make sure it's empty and dry. So if you have some water in there, just give it a few good shakes to make sure you get it all out, and then just measure the mass and then go.
Oh no, my bad. I meant the cylinder types, like the aluminum, acrylic.
Oh yeah, you have to measure the mass of those. Yeah.
Okay.
Yeah, so you determine the volume by measuring the diameter and the height
Okay.
in centimeters, and
Yep.
then you just measure the mass and then calculate the density. Okay.
Okay.
Oh, Jean, I would measure the cylinder before each series because let's say you don't get all the water out for one of them. And so basically you want to make sure that you start with the mass of the cylinder as it is at the minute you're adding liquid to it, not the mass that it was 20 minutes ago. So I would measure the mass of the cylinder each time you add liquid to it, okay? I mean, it only takes like 2 seconds to do, so it doesn't take that much longer. So let's look and see how you would plot that. Okay. So we're at Google. You go to basically just go to Google. Let's just start over. I'm just going to copy these. I'm going to copy this table just to show you how to get there. So I'm going to copy that. And then I'm going to go back to Google. So once we're there, I don't even know if you need an account. I think you probably do, but I think you need an account to save. If you have an account, it automatically saves all the work you're doing there. So that's the reason for having an account. So we just scroll down past docs, that's important, till you get to sheets. That's what we're looking for. You double click on sheets. And geez, sheets just opens right up. Come on. There we go. So we want a new spreadsheet. Just hit blank. And so here's where we get our spreadsheet here. So I had already done data for 0 through 40%. So this is the way you should organize the data for the way you're going to plot it. It should look like this. So you want your volume over here, your volume in one column, and then your masses in additional columns after that. So the one I just did was, I'm just going to type in grape juice. And then I just write my masses in for 5, 10, 15, 20, and 25. Oh, which I need to calculate because I haven't subtracted them. It's important you don't put in the raw numbers, but you subtract the mass of the cylinder, or else you're going to be way off. Your y-intercept will be insane. So my first one is 5.74 grams. $11.34. $16.29. $21.94. And whoops.
Oh, Professor,
Yep.
are you measuring it with the cup or just the liquid itself?
So you measure the mass of the cylinder plus your liquid. But then when it's time to actually plot your data, we're not interested in the mass of the cylinder anymore. We just want the mass of the liquid. So we subtract the mass of the cylinder that we initially measured. So that's what I'm doing here. So these are the masses after I subtract the mass of the cylinder. So my last one here was 56.33 grams, but then I subtract the mass of the cylinder, which was 29.47, and I get 26.86. So I only want the mass of the liquid. Okay.
Okay. Thank you.
So then when it's time to plot these, you just select the numbers. Okay, just select the numbers, just drag across. So now I've got 1, 2, 3, 4, 5, 4, I got 7 columns, right? Now when I do that, basically the first one will be treated as the X axis, and then any additional ones will be treated as Y. Then I just come over to insert, because I want to take this data and I want to insert it into something. So I want to insert it. I want to insert them into a chart. Oops, no, I don't want that chart. Insert them. Oh, here we go. So then we tell it what kind of chart we want. So I'll come over, just got to keep that down here. So I move, so what kind of chart do I want? So when my chart opens up, it'll automatically, this will pop up and say, okay, what do you want to do? What do you want to do with the chart? So I don't want a column chart. What I want is a line, a scatter. I want a scatter chart. A scatter chart just means that each individual point will be represented, and that's what I want. So there we go. So each individual point, we can now see them. Okay, so you see that we've got there's a lot of data here. So it might help to increase the size a little bit to make it a little bit easier to see. So I'll just sort of stretch it out a little bit so we can see it a little better. Okay. Now, we also, so this, we want to connect all these points with a straight line, right? We want each individual group of data to be in a straight line. So what I'm going to do is come over here, click on this. There's 3 dots you can see on the chart here. And it'll say edit. If in case the chart editor isn't open, go on customize, come down to series, because each one of those groups of data is considered a series. Scroll down and say, I want a trend line. Now, the trend line is just, well, it sort of means what it says. It will fit a line in between all those points from each group of data. Now, if it's linear, it'll put a linear line there. If it's logarithmic and goes up like this, it'll fit a logarithmic one. But let's just hit trend line and we'll tell it basically we want a linear fit. Because right below it, you can see what type of fit do you want? Do you want linear? Do you want exponential? Do you want a polynomial fit where you like squares and cubes and all this other thing? No, we don't want anything that fancy. We just want a linear fit. So you can see it looks like we got a pretty good linear fit to all these. But we need to know what the fits are, right? So to do that, I come down, keep scrolling down to label. Now, what do I want to label? Use the equation that you get for the fits. Now, what sort of equation am I expecting to see here? Since it's a linear fit, what am I expecting to see?
Y equals mx plus b.
Exactly. Excellent. Yes, let's see if that's what we get. Yes. Now, weird that I'm getting. Oh, we need. I haven't put in what the. For some reason, it didn't put in the volumes properly. So let's do that. But you can see that each one of these we have y equals mx plus b. You can also say show us the r squared. Now what that says is how good a fit are these data points, and you can see they're excellent. So that really is a linear relationship between those two. I mean, r squared equals 1. We can't really get any better than that. So that means every point is exactly on the line. So that's what you get when you're an excellent chemist, you know, what can I tell you? So I want to change what's on the x-axis, because right now there isn't anything on the x-axis for some strange reason. So what I'll do is go back to customize. And I want to change my axes, my horizontal axis, which is my x-axis. Is it the series I want? Of course, it didn't do this when I did it earlier this morning. It's just doing it now for some bizarre reason. So here, so under chart and axis title, if you want to change the title, for instance, you can change the text to anything you want, like sucrose solution densities, something like that. Remember, you always want to have a title for a plot. Then we want a horizontal axis title. That is going to be volume, mils, and our vertical axis title, which is our y-axis, will be mass in grams. Okay. Now let's see if we can fix this volume, because we're not getting any horizontal axis. Oh, wait a minute. So for some reason, the volumes, they're not showing up properly. I need to figure that out. There we go. That was it. For some reason, so I went under setup, and hadn't happened before. So under chart type, I went down here and it said use column B as labels. So column B, as you can see, is the volume. So column B here is the volume. So when you plot this, make sure that this is checked. Use column B as labels. Now notice that the minute I did that, the slope and the y-intercept all went down by a factor of 5. So why they did that, I don't really know, but this is what you should be seeing. So your volume is here, and then your masses are here. And so the slope of each one of these lines should give you the densities, right? So you can see that with 0%, which is just water, what's my slope?
One x plus negative 0.046.
So what's the slope?
Oh, the slope would be 1.
1, right. So what's my density?
1.
1, yeah. 1 what though?
1 gram per gram per milliliter.
Gram per mil, right. So that would give me, for some reason it doesn't have any decimals after it. So I guess we could only record it as 1 gram per mil, which is good though, because that's exactly what we should get. We should get 1 gram per mil. And then you can see as we add more sucrose, our density changes. So it goes next up to 1.03 mg per mil for 10%, 1.12 mg per mil for 20, and you're going to get different results, but they should be fairly similar to this. 1.19, 1.21, and my grape juice clocks in at 1.06. So another thing you could do is try and figure out, you can plot then the densities of sucrose the percent of sucrose solution versus density. And then you would plot that like, let me share that. I don't think this is included in the lab report, but if you wanted to know what the concentration of sucrose was in your drink, and you can compare it to what the published is, all you would do is just do the percent sucrose versus density, and then look and see. It should be a linear relationship there as well, and then just measure whatever the density of mine was like 1.06 or something, so I would go to 1.56 and then go down and see what the percent sucrose is, and then compare it to the label. I'm going to do that a little bit later. Compare it to the label, and it should be, I don't know, fairly close. You can also check your work by looking online and just looking up a table. I just looked up a table of densities, and here's a table of sucrose solutions, what their viscosity is, basically how thick they are. And then this last one is their density. So this is the density here, the last column. So then you can check your work, like what did you get versus what's been published as the actual density. And we'll see if it's close. Should be fairly close. It won't be exact, of course, but it should be fairly close. And so the other thing you could also do is include the points 0 and 0 in your plot. So go back to your original data, and you can see I've only plotted, just let me move this out of the way. You can see I have, whoops, where did my data go? Oh, up here. You can see with my original data, I've only plotted I've only plotted 5 through 25. If you want even more accurate data, you put down 0 mils and then 0 grams. And that should give you an even better y-intercept and a more accurate slope. Okay. I'm sure you must have some questions about how to use this. So any questions about how to use the graphing function here, or are people just completely confused? I will put a video that one of my colleagues made about how to do this on the YouTube page, as well as this lesson as well. So you can. She does a good job of explaining how to do it. So would you like to review how to do the plotting one more time?
Will this video, where in Canvas would this video be?
Well, I'll put it on the YouTube page and then put links to it on Canvas. Just basically under whatever week it is, this week 4, I guess. It'll be under there. Like lab videos. And I'll also, like where the other lab videos are, and I'll also include my colleague's video as well, because she does a nice job explaining how to use both Google Docs as well as using Excel, if you're going to be using Excel. So should we go? I've got a thumbs up from a few of you. So we should go through this one more time, just to sort of get more comfortable with it.
I think the video will do.
Yeah, I agree.
Okay. Cool.
Yeah.
Anyone have any questions?
Yeah, how do you fill out table 5? Table 3
Table
and 4
5. Let me
pretty
see.
straightforward, but I don't understand table 5.
Table 5. Let me see. Table 5. All right. Table 5. So yeah, table 2 is fairly straightforward. Hopefully you'll get to work on that. 3 are your results.
3 is where the graphs come in, right?
Ah, where's 5? 5. Oh, here we go. Determination of sugar in a beverage. Oh, yeah, like there's a typo. No wonder. There's a typo here. Thanks for pointing that out. So notice what's the problem here? Just have a look at that. Something doesn't make sense. What's
It's
wrong?
Oh, it's just
volume.
Go ahead. Either one.
It's supposed to be milliliters instead of percent.
Yeah, exactly. What the hell is 25% milliliters? That doesn't make any sense. So that shouldn't be there. So this percentage shouldn't be there. It should just be 5. 5 mils, 10 mils, 15 mils, 20, 25. Exactly the way I just did it with my grape juice. Exactly the way you're going to do it with all your sucrose solutions. So this table should look exactly the same. So yeah, with 5 mils of your beverage, what's the mass of the 5 mils of beverage plus the mass of the graduated cylinder? Then you add another 5, another 5, another 5, another 5, write down the mass each time. And then what was the mass of the empty cylinder at the beginning? And you just subtract that for the last column, just the mass of the liquid after you subtracted the mass of the cylinder. That's it. Yeah, thanks for pointing that out. I skipped right past that. That should have jumped out at me. Yeah, percent mils is not a, that is not a unit of anything I can think of. Any other
Oh, can
questions? Oh, go ahead, go right ahead.
can I ask a question about the last lab? Because the
Of
last
course.
post lab question, it was kind of worded oddly.
Okay, what was the question?
Let me pull it up. Sorry. It says, how is an object of known mass called that can be used to establish uncertainty in measurements made with a balance?
Oh, right. Okay. Yeah, that's what's called a standard. So basically, a standard is something that has been measured by a lot of different balances, and you get exactly the same mass. So it basically it's what we would call a reference. So in France, actually, where the metric system was invented, there is a sample of platinum and iridium. There's a little cylinder of platinum and iridium that is under like 3 different bell jars with all the air sucked out of it. That used to be, until a couple of years ago, that was the definition of 1 kilogram. So basically what that meant is that every other kilogram in the world that you would measure would have to be related to that one. So what you would do is basically you take that known mass and you check it against every balance you have, like, and just figure out how close I should be getting exactly like 1,000.0000 grams. And then your job would be to figure out, well, how off is my particular balance? So that's how that would work.
So the answer to that would just be a standard.
Yeah, and then explain how you would use a standard.
Okay, gotcha.
Yeah, so a standard is basically a universally recognized measure of something. So like I said, until recently, it was that block, it was that cylinder of metal. And there's similar blocks. There's one in Washington at the National Institute of Standards and Technology. But now there's a new standard, which involves, like, I forget exactly what it involves, gravity and wavelengths. So that's much more accurate. I can't remember exactly what it is, but it's basically any lab could use this standard to calibrate their instruments, because it's awfully hard to schlep this like 1 kilogram piece of metal around and check everybody, right? That's kind of ridiculous. But we can devise a way of measuring it that everyone can use at the same time. And so so we've swapped that out. But if you have a balance and you want to, like, let's say you're having trouble with it and it needs fixing, you would call like a repair person, a technician would come over, and they would have in a briefcase or something different standards in it, and they would use that to calibrate your balance to make sure it works properly.